When we're looking for organic acids, we're trying to identify positively polarized hydrogens, and normally they're partially charged. Here is an example of a carboxylic acid. It's actually acetic acid. Now, I have said acid twice in the last 5 seconds, so it's possible this might be an acid. But is it a Bronsted-Lowry acid? Let's take a look. The carboxylic acid is donating a proton. So yes, it is a Bronsted-Lowry acid. Notice the arrow, the single arrow. We haven't used the double arrow to show equilibria. This reaction is in equilibria, but normally the equilibrium arrows are only drawn when we want to emphasize the equilibrium issues in a reaction. Chemists can be a little bit lazy in this regard, and I want you to get used to that. Here is an alcohol. The alcohol can also act as an acid, and it's a Bronsted-Lowry acid because it is donating a proton. How does the carboxylic acid and the alcohol compare? Well, it would be great to know their pKa's. Here they are. So, the carboxylic acid has a pKa of 5, while the alcohol has a pKa of 16. From this information, we can say that the carboxylic acid is a stronger acid than the alcohol. We can also say the reaction of the carboxylic acid in equilibria is more towards the right than in the case of the alcohol. That's great. But what would happen if we didn't know the pKa numbers? Could we reason this out any other way? The answer is yes. We often have this problem in chemistry where we have to compare two reactions and work out why one is different from the other. So let's practice here. What's the difference between the carboxylic acid and the alcohol? Well, the difference is a carbonyl. In the carboxylic acid, we have a carbonyl. In the same position of the alcohol, we don't have a carbonyl. So how's that going to change things? The carbonyl allows us to create a second resonance structure from the conjugate base with the carboxylic acid. This means the negative charge is spread over more atoms, and we have a more stable conjugate base. It's more stable, so it's less reactive. So it's less likely to go from the right-hand side of the equilibria to the left-hand side of the equilibria. So the reaction dominates from left to right, more so than the alcohol. Here's another example. This time we're looking at ketone, and we're going to compare that to an alkane. So let's start with a pKa. The ketone pKa is 19. The alkane pKa is 50. So the ketone is a weak acid. The alkane is a really, really weak acid. Wow. So we got that information from the pKa's, but could we have reasoned this out? Yes, we could. Let's have a think about it. In the case of the ketone, and this specific ketone is called acetone, the conjugate base that's created by the donation of a proton can have a second resonance structure. The negative charge is spread over more atoms, and the conjugate base is more stable than in the case of the alkane, which is specifically propane. There is no other secondary resonance structure there. So because of this, in the ketone case, the conjugate base is more stable, less reactive, and less prone in the equilibria to go from right to left than with the alkane. Lastly, I'd like to compare the carboxylic acid with the ketone. So they both have carbonyls, so that's not going to work in terms of working out what's different. Is there anything else? Well, yes, there is. If we look, the hydrogen that will become the proton, in the case of the carboxylic acid, is attached to an oxygen. In the case of the ketone, it's attached to a carbon. How would this affect things? Well, the OH has a bigger electronegativity difference than the CH, which means the hydrogen on the carboxylic acid is more partially positively charged than the hydrogen on the ketone. So if it's more partially positive charged, you don't have to take much more before it becomes fully positively charged, a proton, and it's leaving. So there's, if you will, less to do with the carboxylic acid for the proton to leave. Less energy, so it's a stronger acid, so it's more going from left to right than in the case of the ketone below. Now let's think about organic bases. From a Bronsted-Lowry perspective, the base will accept a proton. But what's doing the acceptance? Well, we've come to see two cases. The first is where we're using a lone pair on the atom to accept the proton, but the atom is a formal negative charge. The convention says here we won't draw the lone pair, but just the formal negative charge. And what we're going to look at now is where there is a neutral species of atom that also has a lone pair. And now here we will draw the lone pair. The lone pair is responsible for accepting the proton. A great example of this is an amine. If you look at the nitrogen atom, it's a neutral species and has a lone pair. We've drawn it. The lone pair accepts a proton. It is a Bronsted-Lowry base. By changing the nitrogen for an oxygen, we go from an amine to an alcohol. But everything else is very similar. The oxygen is a neutral species. We have two lone pairs. One of those lone pairs accepts a proton, and so the alcohol is a Bronsted-Lowry base. But this isn't all an alcohol can do. An alcohol can also act as a Bronsted-Lowry acid. Whether the alcohol is a base or an acid very much depends on the reaction conditions that it's in at the time. Here we have a ketone. The ketone has a neutral oxygen that has two lone pairs. One of those lone pairs can accept a proton. The ketone is a Bronsted-Lowry base. But this isn't, again, all that it can do. It can also be a Bronsted-Lowry acid. And in this next example, you can see the same ketone donating the proton. All these examples use Bronsted-Lowry descriptors. Here we're going to see an example of a carboxylic acid. In this situation, we have two sets of lone pairs. One where an oxygen is singly bonded to the middle carbon, and the other where an oxygen is doubly bonded. Two different oxygen species. But either of those species' lone pairs can react with an acid. Here we see the oxygen that is singly bonded to the carbon, its lone pair reacting with a proton. It accepts the proton. But another situation could be where the oxygen that is doubly bonded to the carbon, its lone pair accepts the proton. And we'll get two different products coming out depending on which oxygen is involved.